So we're studying elliptic curves, which are curves of the form y squared equals x cubed plus ax plus b. So it's only 1 degree higher than curves that you studied implicitly or explicitly earlier, where you had a quadratic here. This was x squared. And then these curves would look like ellipses, parabolas, hyperbolas. With x cubed, it's a little bit different. And if you look at the graph of such a curve in the plane, you'll notice that if x, y solves the equation, which means the same thing as if x, y lies on the curve, then so does x minus y, because you only have a y occurring as a square. So y squared and minus y squared are the same. So whatever the graph looks like, it's symmetric around the x-axis, and it will typically look something like this with maybe a separate component looking like that. So this is one or the other, either just this or these two pieces show you the graph of the curve. And if you take 2 points, say P and Q, wherever they might lie on the curve, it will always be the case, if you draw the line between them, that it'll cross the curve at a third point R. And you take that third point R, you reflect it around the x-axis R prime, and that's what we define to be the sum of P and Q. So this defines an addition operation on the elliptic curve. And we looked at this in R, but we can also define elliptic curve addition . I should also say we can also define elliptic curves in general and additional elliptic curves over finite fields. FP. So let me see if I can find an example. So this is actually the first or one of the homework problems. Exercise 6.5. We have the elliptic curve. So this is 6.5a. The elliptic curve E is y squared equals x cubed plus 3x plus 2. And we want to study this curve over the field with 7 elements. Or Z mod 7Z, if you want to write it as congruence classes. So let's actually do the calculation. So y squared equals x cubed plus 3x plus 2. So in the field of 7, we have 7 elements, 0, 1, 2, 3, 4, 5, and 6. And for each such element, what is y squared? Mod 7. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, which is 2, 4 squared is 16, which is 2, 5 squared is 25, which is 1 mod 7. And 6 squared is 36, which is 1 mod 7. And you'll notice there's always this symmetry. You look at the first half of the numbers, and then the second half, 5 squared is 25 is 4 mod 7. And the second half are the same as the first half, going in the reverse order. So 1, 4, 2, 2, 4, 1. So this is in the field with 7 elements. And what is x cubed plus 3x plus 2? When x is 0, it's 0. When x is 1, it's 1 plus 3 plus 2 is 6. When x is 2, it's 8, plus 6 is 14, plus 2 is 16. Mod 7, 16 is 2. What about when x is 3? 27 plus 9 is 36, plus 2 is 38. Mod 7, that's 3. What about x equals 4? 4 cubed is 64, plus 12, plus 2. 64 plus 14 is 78. Mod 7, 78. Mod 7 is 1. You should check my arithmetic as I'm doing this, because I'm just doing it in my head. When x is 5, 125 plus 15 is 140. 142 is 2. When x is 6, 216 plus 18 plus 2 is 236. 236, I think, is 1 mod 7. Okay, let me just check that. 216, 18 plus 2 is 20. That's 236. 236 mod 7 is 5, I believe. So when do you have a solution of this equation? When x and y are 0, so the solutions. Oops, this is wrong. When x is 0, you get 0 plus 0 plus 2. When x is 0, this is 2. Let me just check again quickly. When x is 1, this is 6. When x is 2, this is 2. When x is 3, 27 plus 9, 36, 38 is 3. When x is 4, 46. When x is 4, 64. 76, 78 is 1. When x is 5, 125. 140 plus 2 is 2. When x is 6, 216 plus 20 is 236. Is 5. So this looks okay. So when x is 2, sorry, when x is 0, this is 2. So the right-hand side is 2. When x is 3 or 4, the left-hand side is 2. We get 0, 3, and 0, 4. When x is 6, there's no y squared equals 6. When x is 2, the right-hand side is 2. The left-hand side can be 3 or 4. So I could have 2, 3, or 2, 4. There's no y squared equal to 3. The 2y squared is equal to 1. So when x is 1, y could be 1 or 6. When x is 5, y can be 3 or 4. So 5, 3, 5, 4. When x is 6, there's no y squared equal to 6. And then we also have the solution 0, 0. Well, point at infinity, point at infinity is a solution. So the number of solutions is 2, 4, 6, 8. It looks like there are 9 solutions if I did this correctly. Now, I'm doing a lot of calculations because elliptic curves, I'm sure, are something completely new to everyone. And it's like you have to learn the arithmetic for these things. Let's look at problem 6.6a. So make the addition table for the elliptic curve y squared equals x cubed plus x plus 2 over f5. So you want to find all the points on this curve and write down the addition table for them. So let's find the, so step 1 is find the curve E of f5. So we have to look at the values. I should actually make sure I include the point at infinity. So you have different values for x, and for each value for x. For each value of x, I want to write down what is y squared and what is x cubed plus x plus 2. So I shouldn't forget the point at infinity, and the other points are 0, 1, 2, 3, and 4. So the point at infinity squared is the point at infinity. And x cubed plus x plus 2 at infinity is infinity. No. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 3 squared is 9, which is 4 mod 4, 4 mod 5, 4 squared is 16, which is 1 mod 5. X cubed plus x plus 2, when x is 0, this is 2. When x is 1, this is 3. When x is 2, this is 8, 10, 12, mod 5 is 2. When x is 3, this is 9, 12, 15, it's 0. Sorry, that's not right. When x is 3, sorry, that's right. When x is 3, this is 27 plus 3. I'm not sure, let me double check my. When x is 0, 0 plus 0 plus 2 is 2. When x is 1, 1 plus 1 plus 2, it's 4. When x is 3, 27 plus 3 is 30 plus 2, 32 is 2 mod 5. When x is 2, 8 plus 2 is 10 plus 2 is 12 is 2 mod 5. When x is 3, 27 plus 3 is 30, 32 is 2 mod 5. When x is 4, 64, 68, 70, I get 0 mod 5. So what are the points on this elliptic curve over the field with 5 elements? So there is the point at infinity. There is when x is 0, there's no y squared equal to 2. When x is 1, you have y squared could be 2, y could be 2, or y could be 3. There's no y squared equal to 2 when x is 4, you can have y equal to 0. So there are 4 points on the elliptic curve. And to find the addition table, I have to add them. Now, adding 0, adding the point of infinity to anything, it's just the point at infinity. Sorry, adding the point at infinity is like the identity. So adding this to any point just leaves the point. So this is the point of infinity, 1, 2, 1, 3, 4, 0, 1, 2, 1, 3, 4, 0. So it looks like we just have to calculate 9 different numbers, but of course addition is commutative. So this equals this, this equals this, this equals this. We just have to calculate these 6 numbers and then we can fill in the rest of the table. So this is an interesting exercise. How do we compute, for example, let's start with this one. 1, 2 plus 1, 3. So on the elliptic curve, E is x cubed plus x, sorry, y squared equals x cubed plus x plus 2 over F5. And I want to compute what is 1, 2 plus 1, 3. Now we can't draw a picture of this because we're working over a field with 5 elements. We're no longer working over the reals where we can do ordinary high school algebra. On the other hand, the rules for addition are exactly the same. So let's just sort of take a picture and recall what things look like. You have a point P and a point Q. You take the line through P and Q and see where it intersects the curve. So what is the line through 1, 2, and 1, 3? Let me start with an easier example. Let's just say 1, 2, and 4, 0. So if this were in the plane, the slope of this line would be minus 2/3. Then we have to write that mod 5. So the line through 1, 2, and 4, 0 is y equals x plus 1. Let me just make sure this is correct. So when x is equal to 4, y equals 4 plus 1, which is 5, which is 0 mod 5. So 4, 0 lies on this line. When x equals 1, y equals 1 plus 1 equals 2. So 1, 2 lies on that line. So the line y equal x plus 1 lies on this curve. So if you substitute x plus 1 for y, you get x plus 1 squared equals x cubed plus x plus 2. X squared plus 2x plus 1 equals x cubed plus x plus 2, or x cubed minus x squared minus x plus 1 equals 0. Now, or this is the same if you like, since you're working mod 5, x cubed plus 4x squared plus 4x plus 1 equals 0. You let x equal 1, you get 0, you get 10, which is 0 mod 5. You let x equal 4, you get 64 plus 64, 128, plus 16 plus 17, 128 plus 17, 145 is also 0 mod 5. So what is the third point on this curve? If I divide x plus 1 into x cubed, sorry, x minus 1, if 1's the solution, x minus 1 into x cubed plus 4x squared plus 4x plus 1. This goes in x squared, x cubed minus x squared, 3x squared plus 4x plus 3x, 3x squared minus 3x. So x cubed minus x squared. The difference is 5x squared, which is 0. Bring down 4x. It goes in 4 times. 4x minus 4, 1 minus, that's 0. So x cubed plus 4x squared plus 4x plus 1 mod 5 is x minus 1 times x squared plus 4. And x equal 4 is the solution of this. X plus 4 into x squared plus 4. This goes in x times. X squared plus 4x. You get minus 4x plus 4. This into this goes minus 4 times. Minus 4x minus 16, which is 0. So x cubed minus x squared minus x plus 1 is equal to x minus 1, x minus 4, x minus 1, x minus 4, x plus 4, which is x minus 1 squared. So we have the double root. So, maybe just to simplify this, I'll just go back and use the formula we worked out last week. So let me just restate that. So in the book, this is theorem 6.6, where you have the elliptic curve E equal y squared equals x cubed plus ax plus b, and you have points P1 and P2 on the curve. And this makes sense whether we're working over the real numbers or over a finite field. So this is really just writing down what you do when you solve by hand, drawing the line through 2 points to find the point of intersection, the third point on the curve, reflecting it through the x-axis and defining that as the sum. So P1 and P2 points on the curve. If P1 is the point at infinity, or P2 is the point at infinity, then P1 plus P2 is the point at infinity. Otherwise, if neither of them is the point at infinity, P1 has coordinates x1, y1. P2 has coordinates x2, y2. And if they are symmetric points, so if x1 equals x2 and y1 equals minus y2, then P1 plus P2 is the point at infinity. On a curve, this point would be x1, y1, x2 equals y1, but y2 is minus y1. So these are the symmetrically opposite points on the curve. One is the negative of the other, and they add up to the identity, which is at infinity. Okay. Otherwise, define lambda as follows. Lambda is going to be the slope of the line joining the 2 points in the usual sense, y2 minus y1 over x2 minus x1, if P1 is different from P2. So we don't have x1 equals x2, so this is a non-zero denominator. But if P1 equals P2, I can't take x1 equal x2, but I have, this will be 3x1 squared plus a over 2y1. And then x P1 plus P2 is the point x3, y3, where x3 is lambda squared minus x1 minus x2, and y3 is lambda times x1 minus x3 minus y1. So these are the formulas you have to remember. And during an exam, since the exams are open book, you don't have to remember them. They're written down in the book. Okay, so let me go back to the problem that I started with. I want to compute the addition table for a certain elliptic curve over F5. So I had the following. my elliptic curve is y squared equals x cubed plus x plus 2. And the points on the elliptic curve over f5 are the following. There's always the point at infinity. And I have 1, 2, 1, 3, and 4, 0. 1, 2, 1, 3, 4, 0. So let me try and fill in this table. So adding the point at infinity, which is just the additive identity to a point, is just that point. What about 1, 2 plus 1, 2? So our rule said if P1 equals P2, then lambda, so this is the case, P1 equals P2, lambda is 3x1 squared plus a. A is equal to 1. B is equal to 2. x1 is 1. So this is 3 times 1 squared plus a over 2 y1. y1 is 2. 2 times 2. This is 3. This is 4 over 4 is 1. So if lambda is 1, then x3 is lambda squared minus x1 minus x2. 1 squared, x1 and x2 are both 1, is minus 1 at 4. And y3 is lambda 1 times x1 minus x3. x1 is 1 minus x3 is 4 minus y1, which is 2. So that's minus 3 minus 2, that's minus 5, which is 0. So the point 1, 2 plus 1, 2 is 4, 0. What about 1, 2 plus 1, 3? So in this case, what is this? Oh, this is easy because this is 1, 2, and modulo 5, 3 is minus 2. And in the case when x1 equals x2 and y1 is minus y2, the sum is the point of infinity. It's the point of infinity. So 1, 2 plus 1, 3 is the point of infinity. By commutativity, 1, 3 plus 1, 2 is the point of infinity. What about the point 1, 2 plus 4, 0? So for 1, 2 plus 4, 0, P1 is different from P2. Lambda is y2 minus y1 over x2 minus x1. So that's minus 2 over 3. Minus 2 mod 5 is the same as 3. 3 over 3. This is 1. So lambda is 1. So x3 is lambda squared, 1 squared, minus x1 minus x2. That's minus 4, which is 1. y3 is lambda, which is 1, times x1 minus x3. x1 is 1 minus x3, which is 1. minus y1 minus 2. So that's 0 minus 2 is minus 2, which is the same as 3. So 1, 3. So 1, 2 plus 1, 3 is 1, 3. Actually, this is really just confirming everything is right, because on each line you have to have just a rearrangement of your points. So this has to be 1, 3. 1, 3 plus 1, 3. So again, when P equals Q, so in P1 equals P2, lambda is 3 times 1 squared plus A, which is 1, over 2 times y1, 2 times 3. Let's see if this is right. 3 times 1 plus 1, this is 4 over 6. 6 is the same as 1 mod 5, so lambda is 4. So x3 is 4 squared minus 1 minus 1. 16 minus 2 is 14, which is 4. Y3 is lambda 4 times x1, 1, minus x3, 4, minus 3. That's 1 minus 4, this is minus 12, minus 3 is minus 15, which is 0 mod 5. So 1, 3 plus 1, 3 is 4, 0. See, if this is 1, 3, 1, 2 plus 4, 0, then this is also 1, 3. Okay. What is 1, 3 plus 4, 0? This is really just a check that we're doing this correctly, because this has to be the last remaining point, 1, 2. So if 1, 3 plus 4, 0, lambda is y2 minus y1, 0 minus 3, over x2 minus x1, 4 minus 1, minus 3 over 3, which is minus 1, which is 4. And so x3 is going to be lambda squared, 4 squared, minus x1 minus x2, minus 1 minus 4. 16 minus 5 is 11, which is 1. And y3 is lambda 4 times x1 minus x3, which is 1, minus y1, which is 3. So that's minus 3, which is 2. So x3, y3 is 1, 2. Which is, again, what it has to be. And this is 1, 2. The symmetric place is 1, 2. The last is 4, 0 plus 4, 0. That has to be the point of infinity, because it's the only thing. Let me actually calculate that and see what happens. So we're taking 4, 0 plus 4, 0. Oh, but it's what it said. If x1 equals x2 and y1 is minus y2, it's the point of infinity. So we get it right here. So this is a good exercise in learning, just a good practice, working with elliptic curves over a finite field. This is the addition table. Okay, now, where does cryptography enter into this? So you remember, for example, for Diffie-Hellman, we had the discrete logarithm problem. We had G is a primitive root mod P, And we're given G, given the prime P, G and H. The discrete logarithm problem is compute the logarithm of H to the base G, that's some number X, such that G to the X equals H, or G to the X is congruent to H mod P, if you prefer. Another way to state this is compute X such that H equals G times G times G times G, H times. So X times. That's the discrete logarithm problem that was the basis for a number of our cryptographic methods. Based on the fact that FP star, which is the finite field without zero, is a multiplicative group. And given a number G and a number H, or an element, two elements G and H of this group, the question is, how many times do you have to multiply G by itself to get H? That's the logarithm. Now, the analogous problem for cryptography based on the elliptic curve is the following. E of FP, which is the group of points on the elliptic curve E in the field FP, this is an additive abelian group. And we can pose the question, given points P and Q in this group, compute X, a positive integer, such that if you add P to itself, X times, you get Q. Adding P to itself X times, this is X times P. And maybe instead of using the letter X, I'll just use the letter N. Compute a positive integer N. So you add P to itself N times to get Q. What is N? It's completely analogous to the discrete logarithm problem in finite fields under ordinary multiplication. How many times do you have to multiply G by itself to get H? Here the problem is, how many times do you have to add P to itself to get Q? That's the discrete logarithm problem for elliptic curves. And N we write as the log of the point Q with respect to the point P. It's completely analogous to here, where we wrote the log of the number H with respect to the number G in the finite field. Here is the log of the point Q with respect to the point P in the elliptic curve. And this is the number N of times you add P to itself to get Q. And so this is N additions on the elliptic curve. So this is what is called the elliptic discrete logarithm. And now There's one thing you have to be careful about, and that is, so this is usually called the acronym ECDLP, elliptic curve discrete logarithm problem. Given the problem is, given P and Q, find this discrete logarithm N. Find the number of times you add P to itself to get Q. Okay. Now, this is not completely precise because the elliptic curve, E, if you look at it over a finite field FP, this is an abelian group, but it's finite. If this group has order S, if E of FP has order S, that means contains S elements. E of FP, the cardinality of that group, the order of that group is S, then SP is the identity for all P. So that means that if NP equals Q, then N plus SP equals Q, because this is NP plus SP, but SP is the identity, the point of infinity, and you still get Q. So the function from E of FP to E to the integers, this is the log of Q to base P, isn't completely well defined. It's really a map into the integers mod S, because if NP equals Q, then N plus SP equals Q. So you really want to think of N as a congruence class mod S. And when you do that, everything falls very nicely in place. And you have the addition rule that you hope to find for any logarithm, that the log of Q1 plus Q2 to base P is log of Q1 plus the log of Q2. What this says is the following. If N1P equals Q1 and N2P equals Q2, then N1 plus N2P, you add P to itself N1 times, N1 plus N2 times. That's N1P plus N2P. That's Q1 plus Q2. So the log of Q1 plus Q2 to the base P is N1 plus N2. But N1 is the log of Q1 to base P, and N2 is the log of Q2 to base P. So log P as a function from the elliptic curve to the integers mod S is actually what we call in algebra a homomorphism. The log of the sum is the sum of the logs. Log Q1 plus log Q2 is the log of Q1 plus Q2. So this is the very nice formula that we have for the logarithm. Now, one difference between mathematics classes and computer science classes is that in mathematics classes, you are happy to learn how to solve the problem. In computer science, that's not enough. It's not enough to know how to solve the problem. You have to know that, in fact, a computer, once it starts to solve the problem, will give you an answer before you die from old age, let's say. Or if that's not that far away, until the Earth disappears and the sun burns out. As you worry about how long the calculation takes. So we have to find efficient methods to compute addition in the elliptic curve. So let's remember there is a way to do multiplication easily, mod p. We had a system called square and add. Right? So let's just recall. Suppose you want to compute a to the n mod p. So one method, which is bad, is to start to multiply a times a, multiply that by a, and keep going. And that takes n multiplications, actually n minus 1 multiplications to compute a to the n. Just compute a squared, a cubed. You multiply a by itself n minus 1 times, you get a to the n. So this is bad. What is better is to take n and express it in binary. Epsilon 0 plus epsilon 1 times 2 plus epsilon 2 times 4, epsilon k times up to 2 to the k. Write the binary expansion. And how many terms are there? Well, if 2 to the k is bigger than n, then the coefficient is going to be 0. So how far out do you have to go? How many powers of 2 will occur in the binary expansion? The largest power of 2 will be when 2 to the k is less than or equal to n, but strictly less than 2 to the k plus 1, which means k is less than log n to the base 2, which is less than k plus 1. So the number of k's you're going to need here is, so the number of powers of 2 is roughly log n to the base 2, which is much smaller than n. And why is that enough? So let's just recall, how do you compute how do you compute a to the n? So compute a to the n. Bad way, multiply a by itself n minus 1 times. So you have to do n minus 1 multiplications. Multiplications take time, cost money. You want to reduce the number of multiplications that you're doing. Better way, write n as a0 epsilon 0 plus epsilon 1 times 2 epsilon 2 times 2 squared up to epsilon sub k 2 to the k, where k, so here the k is roughly log n to the base 2, within one of them. Compute multiplications. Compute. A squared. How do you compute a squared? That's a to the first power times a to the first power. Compute a to the fourth. That's a squared times a squared. It took one multiplication to get a squared. It takes one additional multiplication to get a to the fourth. A to the eighth, you multiply a to the fourth by itself, you get a to the eighth. You get a to, this is a to the 2 cubed. You get a to the 2, a to the 16th, a to the 2 to the fourth. That's a to the 2 cubed times a to the 2 cubed. That is a to the eighth times a to the eighth is a to the 16th. So how many multiplications to get a to the 2 to the k? That's as far as we want to go. A to the 2 to the k is a to the 2 to the k minus 1 times itself. So you take a, you square it. You square it again. So you have how many multiplications? A squared. Then a squared squared. That's a to the fourth. Then a to the fourth squared. That's a to the eighth. Then a to the eighth squared. That's a to the 16th. Finally, you get a to the 2 to the k minus 1, and you square it, you get a to the 2 to the k. So to get all these powers takes k multiplications. Where k is the log of n to the base 2. So you do k multiplications, you get these numbers. And then what is a to the n? A to the n is a to the epsilon 0 plus epsilon 1 times 2, epsilon k 2 to the k. This is equal to a to the epsilon 0. That's either 0 or a squared to the epsilon 1, a to the fourth to the epsilon 2, up to a2 to the k to the epsilon sub k. So these epsilons are 0 or 1. If they're 0, they're not, ignore them. The worst you can have is when you have to multiply all these together. There are how many multiplications here? K multiplications. So it took k multiplications to get the powers of a, and at most k multiplications to get a to the n. So we can compute a to the n in at most 2k, which is 2 log of n to the base 2 multiplications. As opposed to n multiplications, if you just multiply a by itself n times. So this squaring and multiply algorithm is extremely efficient for taking powers of another. Now we can carry this over to addition. Suppose I want to compute n times a. How many addition steps do I need? I could take a, add a to itself to get 2a, add a to 2a to get 3a, add a to 3a to get 4a. And in general, we'll take n minus 1 additions to compute an a. So if additions are what is going to cost money, this is going to be bad because it takes roughly n steps. What is better? Let's see if we can find an analog of the square and multiply. So suppose I want to compute a plus a, which is 2a plus 2a. Again, this is one addition. 2a plus 2a, which is 4a, is one addition. 4a plus 4a, which is 8a, is one addition. So this is, which is 2 cubed times a. So in general, if I want to get 2 to the ka, if I want to get all the multiples of a by powers of 2, a, 2a, 2 squared a, 2 cubed a, up to 2 to the ka, this is going to take each step, each of these is one addition, it's going to be k additions. And I want to go as far where 2 to the k is less than n, but less than 2 to the k plus 1. So k is going to be log n to the base 2 at most. So this is going to take, at most, log n to the base 2 additions. And now I take my number n, and I write it in binary. So n is summation epsilon I 2 to the I goes from 0, you go up to at most k. So if I want to add a to itself n times, n times a is summation I goes from 0 up to k, epsilon I 2i 2 to the I a. So I'm adding powers of 2 times a to itself. So I have some additional additions here. K plus, I have k additions. I have, this is epsilon 0 a plus epsilon 1 2a plus epsilon 2 2 squared a up to epsilon k 2 to the ka. I take 1, 2, 3 up to n, k additions. So altogether, 2k additions to compute NA, which is 2, at most 2 log n to the base 2 additions, which is much better than n additions. Right? I mean, you know that from calculus, the limit of log n over n, as n goes to infinity, is 0. So when n is large, log n is much, 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 much smaller than n. You're doing many fewer additions by this double and multiply, double and add method. And it's completely analogous to the square and multiply method for computing powers. We can actually do better than that. We can reduce this by at least a half by observing the following. You see, in binary addition, we write a number n as summation epsilon I 2 to the k, where epsilon I is 0 or 1. So, and this takes the number I goes from 0, or let's say 2 to the I, or yeah, 2 to the I goes from 0 up to a number k, where k is log n to the base 2. see. So suppose n is, this is just an example in the text, 947. How do we write 947 in binary? So what are the powers of 2? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. This was already too big. So the largest power of 2 will be 512. This is 512 plus 435. The largest power of 2 and 435 is 256. This is 512 plus 256 plus what do we add to it? 256 to get 435? 44, 179, I think. $179, the largest power of 2 in that is 128. This is 512 plus 256 plus 128 plus 51. The largest power of 2 there will be 32. 512 plus 256 plus 128 plus 32 plus 19. We get 512, 256, 128, 32. 19 is 16 plus 2 plus 1. So we have 947 in binary is 1 plus 2 plus 2 to the 4th power plus 2 to the 5th power plus 2 to the 7th plus 2 to the 8th plus 2 to the 9th. So if we had to compute 947 times A, we would just have to compute the multiples, the power multiples of A. Right? There are 10 of them, actually 8 of them, 9 of them, and then do another 9 additions. Right? You have to compute these multiples of A and then A. But there's so instead of having to add A to itself 947 times, we would end up with at most 20 additions. But we can even make that less if we make the following sneaky observation. What is 2 to the 4th plus 2 to the 5th? 2 to the 4th plus 2 to the 5th is 2 to the 4th plus 2 to the 5th is 2 to the 5th plus 2 to the 5th minus 2 to the 4th. Is that right? Because this is 2 to the 5th minus 2 to the 4th is 2 to the 4th. 2 to the 5th plus 2 to the 5th is 2 to the 6th minus 2 to the 4th. So let me just plug that in here. I mean, you might say they haven't done very much. This is 1 plus 2 minus 2 to the 4th plus 2 to the 6th plus 2 to the 7th plus 2 to the 8th plus 2 to the 9th. Here we have 1, 2, 3, 4, 5, 6, 7 terms. Here we have 1, 2, 3, 4, 5, 6, 7 terms. That hasn't helped us very much. But now we have these 4 consecutive powers of 2. And let's make the following sneaky observation. 2 to the 6th plus 2 to the 7th plus 2 to the 8th plus 2 to the 9th is minus 2 to the 6th plus 2 to the 6th. That's just 0. Plus 2 to the 6th plus 2 to the 7th plus 2 to the 8th plus 2 to the 9th. I just added 0 to this. But this is minus 2 to the 6th. 2 to the 6th plus 2 to the 6th is 2 to the 7th. plus 2 to the 7th plus 2 to the 8th plus 2 to the 9th. This is minus 2 to the 6th. 2 to the 7th plus 2 to the 7th is 2 to the 8th, plus 2 to the 8th plus 2 to the 8th, plus 2 to the 9th. 2 to the 8th is plus 2 to the 8th is 2 to the 9th. 2 to the 9th plus 2 to the 9th. 2 to the 9th plus 2 to the 9th is 2 to the 10th. So this is equal to 1 plus 2 minus 2 to the 4th minus 2 to the 6th plus 2 to the 10th. So here, instead of 1, 2, 3, 4, 5, 6, 7 terms, I have 1, 2, 3, 4, 5. This is much shorter. If I wanted to compute 947a, here I would have used 9 doublings plus 1, 2, 3, 4, 5, 6, 7 numbers out of 6 additions. This would have taken 15 steps. Here I have 10 doublings, 1, 2, 3, 4, but only 4 additions or subtractions. That's 14. That's a smaller number. And the point of this story is you can actually do better than just expressing a number in binary to speed up additions. Suppose we use a kind of a refined binary representation where we can write n as a sum at, well, powers of 2. But where epsilon 0 is 0 or 1 or minus 1. If we allow some minus ones here, we can actually contract, we can actually reduce the number of steps we need to find a solution. So let me express it like this, and this is actually a very nice theorem. Suppose that let k be the log of n to the base 2. So 2 to the k is less than or equal to n is less than 2 to the k plus 1. So we can write n in binary. N is summation epsilon I 2 to the I goes from 0 to k, where epsilon I is 0 or 1. I should have called these something different, like these. But also, this is better, we can write n as summation u sub I 2 to the k. I goes from 0 up to k, where u sub I is 0 or 1 or minus 1. And the number of steps here, additions or subtractions, every time ui is 0, the number's not there. If this is a 1, you add. If it's minus 1, you subtract. Where the number of u sub I, different from 0, that is plus or minus 1, is at most a half of k. So you can reduce the number. If you allow a minus 1 instead of a plus 1, you can actually reduce the number of terms in this set. And the proof is a kind of algorithm. So suppose you take the binary representation for n. and it's epsilon 0 plus epsilon 1, 2 plus epsilon 2 times 4 up to epsilon sub k 2 to the k, if you like. And I suppose a string of these are ones. Like suppose you have epsilon s plus 1 up to s plus t minus 1 all equal to 1. So in this representation, you have 2 to the s plus 2 to the s plus 1 plus 2 to the s plus 2. All these consecutive terms with the 2 to the s plus t minus 1. If you add a 2 to the s to this and subtract a 2 to the s, this is going to be equal to minus 2 to the s plus 2 to the s plus t. So we have this formula. And if you have consecutive 2's, you can replace it with a much shorter expression where you allowed a minus sign. So in particular, if you had even 2 consecutive 2's, you would replace it by something where the powers differed. Like if this were s and s plus 1, this would be s plus 2. You can always use this rule to write n as summation ui 2 to the I, where you do not have 2 consecutive terms appearing. So ui plus 1 is always 0. If you have 2 consecutive terms, one of them has to be 0. So there'll be a couple of homework problems just to work this out, but it really is very interesting. That is, if you modify your binary expansion, so you have plus 1's and minus 1's as coefficients, you can always shorten the number of powers of 2 you need to represent them. You can always avoid consecutive non-zero terms. So from 0 to k, you would have at most k over 2 plus or minus 1's. And that's another way to speed up the computation of inaddition. And efficient computation is not just a computer science problem, it's an extremely interesting mathematical problem. And mathematicians, even those who are not computer scientists, study this in great detail. And there are lots of interesting questions of this sort. In linear algebra, you multiply matrices, and it's an extremely difficult problem in computation to multiply matrices efficiently. If you do it the way you're taught in linear algebra, to multiply 2 n by n matrices is going to take n cubed multiplications. If n is big, n cubed is humongous. You don't want to do n cubed multiplications. So there's a question of how can you multiply 2 matrices in, let's say, n squared multiplications. And these are really extremely hard problems that no one can solve. Anyway, that's it for today.
Thank you.
I might post another extra lecture or 2 over the weekend because there's not a lot of time until the final. So
Thank you,
the earlier I
Professor.
can do things, the more time you have to study it.
And Professor, quick question. For like the final review, will we probably get like this Sunday, like how we got the midterm one, like over the weekend, or will it probably be like around like Monday and we'll have like a couple days to work up?
I'll try and do it over the weekend.
Okay.
I'll try and do it. But you understand, like Monday, Tuesday, and Wednesday is supposed to be the equivalent of 3 weeks of work in a regular semester. So I have to sort of like have that. That's why I want to try to get some lectures done in advance.
All right. Thank you, Professor.
Okay. All right. Bye-bye. Have a good weekend.
You too.
You too.
Thank you.